Okay, good morning, everybody. Welcome to another episode of Physics 1510. Today, we're going to talk about fundamental interactions. And what does fundamental interactions mean? Sometimes they're called fundamental forces. Well, it appears like to us like there's lots of different kinds of forces. There's friction, and there's gravity, and there's spring forces, and there's compression forces, and there's tension forces where we pull on things and whatnot. But we can boil them down to a combination of only four kinds of forces that we consider really fundamental. And everything else is kind of composed of lots of those added together. And what physicists think is that we can classify these four interactions as very fundamental. One of them is the gravitational force. So gravitational forces involve anything that has mass. So fundamental forces. Any objects that have mass. So that's most of the matter we know about. That's you and the Earth and stars and books and planets and bacteria and protons and electrons. So anything that has mass. There's a force that we call electromagnetic. And this affects anything that has electric charge. And since we're made up of atoms, and atoms are made up of charged particles like protons and neutrons, everything we're made up of has charge. And so this is a very important force that basically holds the world as we know it together. Now, this electromagnetic really has two pieces. There's electric and magnetic. Even though the electric and magnetic forces are related. This semester, we're going to talk a lot about the electric force, but not about the magnetic force, which we're going to leave until next semester. There is a force called there's the gravitational force, there's the electromagnetic force, there's a force called the strong force. And the strong force affects anything that's made of quarks. So what's a quark? Well, a quark is a subatomic particle that, in combinations of different quarks, is what makes up particles like protons and neutrons and a bunch of other less well-known particles. Protons and neutrons are each made of, we think, 3 different quarks. And a quark can have, turns out to have charge of something like plus or minus 1/3 of an electron charge, or plus or minus 2/3 of an electron charge. But it doesn't affect things that aren't made of quarks. Things that are made of quarks are called hadrons by physicists. Things that aren't made of quarks are called leptons, and they include things like electrons, neutrinos, which have no electric charge, and muons. There are a lot of them. We got pions over here. So there are a lot of particles. Yeah, there are different kinds of quarks are called have attributes that are called up, down, charmed, and strange. And we're not really going to talk about that very much in this course, but if you're interested, this is all part of what's called the standard model that describes all the interactions that go on in nuclear physics and elementary particle physics. The strong force is actually very important to us because it's what holds protons and neutrons together in the nucleus. As you probably know, protons have positive electric charge, and so they repel each other actually quite strongly with the electric force. And we need something to hold them in place to make up an atomic nucleus. And that is the strong force. That's why it's called the strong force. And finally, there's another force called the weak force. It affects everything, but not very much. And so it's actually hard to observe this force. One example of the weak interaction is that there are a lot of particles called neutrinos, which are little, very, very low mass neutral particles that are produced in lots of nuclear reactions. So we have a big stream of neutrinos coming from the sun, for example. And they interact, they have almost no mass. For a long time, physicists thought they had no mass, but now we know they have a mass, but it's tiny. They don't have any electric charge. They're not made of quarks. And so they almost don't interact with anything. They interact so rarely that they stream right through the Earth and go out the other side without actually interacting with anything. They're streaming right through you now. Except very rarely they do interact. And that's how we can detect them, by catching these really rare interactions. And we know they exist. But other forces like spring forces or contact forces or whatnot are just combinations of these forces. In fact, why can't you push one hand through the other hand? Well, when you get right down to it, it's the electrons in the atoms in your finger that are repelling the electrons in the atoms in your other finger, and they repel each other. And so it's the superposition of lots of electric forces. We're going to concentrate in this chapter on two examples of the fundamental forces. We're going to talk about the gravitational force, one of the most important forces we know, and the electric force, also an extremely important force. And we're going to learn to calculate them, to use them to predict motion, to do all the things that we've done with forces up to now. So let's talk about the gravitational force. If we have two massive objects, 1 and 2, the gravitational force is always attractive, so they attract each other. Force on 1, so 1 is attracted by 2, and 2 is attracted by 1. And the force acts along a line. Why does gravity exist? I think at base we don't know. So there are physicists who are trying to come up with a theory of everything, which would unify all of these forces, and some progress is made in unifying the electric, the strong and the weak force, but no one's quite sure about gravitation. At base, I don't think we have an answer for that question. It just does in our universe. But what we can do, even with the tools we have here in introductory physics, is describe it, to probe its behavior, to see if we can use our description of it to make models of this of systems that actually predict what happens with them, and keep looking to see if we can find a deeper unity among all these kinds of interactions. No, I think, Peyton, you're fine. The chat gets saved, so. So the gravitational force between two objects, 1 and 2, is clearly it's going to be a vector. It acts along the line between the forces, between the objects. It depends on the mass of the object. So along the line between the centers, depends on mass. It depends on distance. So the closer things are, the stronger the force is. So it depends on distance. And we can write this force mathematically as a vector, F gravitational. So we'll calculate on 2 by 1 has this mathematical form. There's a minus sign. There's a constant capital G. We have the mass of object 1 and the mass of object 2, the product of these two things, divided by the magnitude of the relative position vector squared times the vector r hat. And so let's break this down piece by piece and see what this equation means and if it makes sense. So first of all, we need the constant. The constant capital G is equal to 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. Now, we know what the mass of object 1 is and the mass of object 2 is. And having this product here, this M1, M2, says that, what does that tell us about the force? Well, if M1 gets bigger, then the magnitude of the force gets bigger. If the mass of object 2 increases, then the magnitude of the force increases. So if the mass of either object is bigger, the magnitude of the force goes up. If the object of either mass is small, the mass of either one is smaller, that goes down, okay? And that's why they show up in the numerator. And it depends on both of them. Now, the magnitude of r squared. What's the vector r? Well, the vector r is defined as going from the object in the surroundings to the system. So the thing that experiences the force and this causes the force. So in this case, since we're chosen object 2 as our system, the vector r would go from the center of object 1 to the center of object 2. So that would be our vector r. So r from center of object in surroundings to center of our system. And so the magnitude of r is, of course, just the distance then between these two objects, center to center. And r hat, of course, is just a unit vector in the direction of r. So r hat would be a vector like that up here in our diagram. And we see that the minus sign was needed to give us the correct direction. In the case of a gravitational force, because if 2 is our system, if we look at our diagram up here, so 2 is our system, then the vector r hat here is pointing from the surroundings to the system. But the force on 2 is actually in the other direction. So that's what the minus sign is for. Okay. So let's see if we can apply what we know here about this equation to answer a few simple questions to start out with. All right. So here's our first question. Let's consider a planet that has several moons. The gravitational force exerted by a planet on one of its moons is 3 times 10 to the 23 newtons when the moon's at a particular location. If the mass of the moon were 3 times as large, what would be the force on the moon? So remember, let's write our equation here. The gravitational force is equal to minus g, mass of object 1, mass of object 2, the distance squared, r hat. Okay. So given that equation, our description of that equation, what can we conclude about what happened to the force? So answering these questions is an important part of being engaged with what we're doing here. You don't get penalized if you're wrong, but actually trying to apply what we've just been talking about is really a key piece of mastering this material. So take the risk, answer the question. All right, so let's see what you said. So by far the biggest majority said 4. So let's see if that's correct. So the magnitude of the force is just going to be the absolute value of g m1, m2 over the magnitude of r squared times the magnitude of r hat, which is 1. So this is case A. Case B, where the magnitude of the mass of the moon is 3 times bigger. So we have 3, we now have a 3m1 in our equation. So in fact, the force is going to end up being three times bigger, and so in fact, that's the right answer. So Marco asks, is the magnitude just equal to this first piece without the minus sign? And of course it does work out that way, because so magnitude of F is the absolute value of minus G M1 M2 over the magnitude of R squared times the magnitude of R hat. Well, that's just equal to 1 because it's a unit vector. And the absolute value of a scalar quantity is just the quantity without the minus sign. And we know that G is positive. We know that masses are positive. We know that a distance is a positive number. So in fact, we do end up getting G M1 M2 over the magnitude of R squared as the magnitude of F. Okay. So let's rewrite our equation here. The gravitational force is minus G M1 M2 over the magnitude of the vector R squared R hat. The second question is, so the magnitude of this force between the planet and the moon is 3 times 10 to the 23rd newtons when the moon is a particular location. If the moon were twice as far away, if it were in an orbit twice as far away, what would be the force on the moon then? So look carefully at this equation. So now we aren't quite so convinced. There's a slight majority saying 4 is the answer, but a fair number of people say 3. So let's see how we think about this question. 4 is correct, actually. So let's see how we think about this question. So we're interested in the magnitude of the force here. So in the first case, the magnitude of force 1 is going to be a G M1 M2 over the magnitude of R is the distance, right? So the magnitude of R squared. In the second case, when it's farther away, we're going to have a G M1 M2 over 2 times the magnitude of R squared, which is equal to a G M1 M2 over 2 squared times the magnitude of R squared, which is equal to G M1 M2 over 4 times the distance squared. So in fact, the force is going to go down by a factor of 4. And so we're going to get 3/4 times 10 to the 23rd. Sorry, it's ragweed. 3/4 times 10 to the 23rd is our final answer. So this is very important. This is the behavior of a 1 over this R squared force, and we're going to see that the electric force has exactly the same kind of distance dependence. It's going to look and form very much like this. So this is called a 1 over R squared force, and when you double the distance, the force goes down by a factor of 4 because of the square in the denominator. Well, we are using the unit vector lay. So we are using, we talked about that up here, right? So the magnitude of the force, so if we look at this equation here, we say the magnitude of the force is the absolute value of the scalar part times the magnitude of the unit vector. but the magnitude of a unit vector is 1. So basically the magnitude of the unit vector here is, we're multiplying by 1 in both cases when we're talking about magnitude. Okay, one more question. Let's see if I can, here we go. Let's make sure we know what r hat really is. So we want to find the gravitational force on the planet by the star. Okay, so our system is the planet, because that's what's experiencing the force. The star is the thing in the surroundings that's causing the force, right? So what is the direction of the unit vector r hat? So we have a question of what's the point of the unit vector in the equation? Well, the unit vector gives the direction. In the vector equation, the unit vector gives a direction. Remember that unit vectors have no units because it's the vector divided by its magnitude, and they both have the same units. So unit vector has no units. So its only purpose in life is to give a direction. And so it's a key part of the vector equation for the force, but when we take the magnitude of a unit vector is 1, so it doesn't affect the magnitude of the force. So we're looking at, so are they motionless? We're looking at an instant. So anytime in physics we say, what is the force? What is the direction of the force or something? We're implicitly saying at the current instant. Now we know that if we think about the Earth, for example, it does move around the star, but it takes it 365 days to go around, so that in a short time, that's a very short time, a few seconds, it's not changing much, but we always mean at this instant. What's the force at this instant? So what's the direction of r hat at this instant? These are the results. And the majority is wrong. Yeah, exactly, Hunter. That's right. So it goes, the vector r goes from the surroundings, the object in the surroundings that's causing the force to the system. And since we want to know, so we have to parse this statement a little bit carefully. If we say force on the planet, okay, that tells us that the planet is the thing experiencing the force, so this is the system. And that must mean by the star, that's the surroundings. So the vector r goes from the star to the planet. Yes, Kate, I think that's a great way to think about it. I always think about its final minus initial. And the way so we can think about that, suppose we have an origin here, and so this is r star, and this is r planet. Then the vector r is just r planet minus r star. The minus sign doesn't flip the direction of anything except the force. I mean, you can think of the minus sign as being added there in the end to get the direction right. But if we look at this equation here, minus g m1 m2 over magnitude of r squared r hat, all the pieces have mathematical meanings. So the equation doesn't, the minus sign here doesn't make the mass of m1 negative. It doesn't make the mass of m2 negative. It doesn't change the magnitude of r. It doesn't change the direction of r hat. It changes the direction of the final vector. So the minus sign is applied to this whole vector, and I think that's the correct way to think about it mathematically, actually. So here's the direction of r hat. Okay, so Peyton is asking, why did we define the vector r that way and not the other way, basically? You wouldn't need a minus sign if you defined the vector r that way. We define the vector r going that way to be consistent with the electric force, and more importantly, to be consistent with something that's going to be extremely important next semester, the concept of electric and gravitational field. And so in those cases, basically we have surroundings but no system necessarily. And so the vector r always starts on the object in the surroundings. So we're looking ahead a couple of months here and defining r in a way that we're never going to have to change our minds or relearn how to define it or redefine it or something else. We're always going to define it exactly this way. So that's a good question. Now, if you get this backwards, you're going to have your gravitational forces going in the wrong direction. So you would end up, instead of having the force on planet going toward the star, you would have the force on the planet going away from the star, which would mean that the planet would be repelled by the star. So instead of getting orbits, which you'll do computationally, you would actually get a planet veering away from a star. No, Joseph, it's going to end up being more complicated than that, and we'll see it next time. It doesn't mean that there's always going to be a minus sign, because the direction of a force depends on the sign of lots of things. It depends on the direction of this force depends on the sign of M1 and M2. And we know that mass is always positive. There's no such thing as negative mass. But when we get to electric charge, that's going to be very different, because there's going to be a charge of a proton or electron. Electron has a negative charge, a proton has a positive charge. And so this whole scalar piece here is going to have a sign, and we don't need a minus sign. So we're defining it in a way to make it, we're defining it for gravitational forces in a way so that it's consistent across gravitational and electric forces. That's a good question. Let's say we have two objects, a star whose location is 0.5 times 10 to the 11, 1 times 10 to the 11, 0 meters relative to something. And a planet whose location is 2 times 10 to the 11, 1.5 times 10 to the 11, 0 meters. And the mass of the star is 1 times 10 to the 30 kilograms. Stars are pretty big. And the mass of a planet is 5 times 10 to the 24 kilograms. And what we want to do is put this all together and actually calculate the gravitational force. So find the force on the planet by the star. So we know what we need to do here. We're going to take our equation for the gravitational force minus g, mass of the star, mass of the planet, magnitude of the vector r, so the distance between them, direction of r hat, and we're going to calculate that. Now we could do that by hand, but I'd actually like to show you an easier way to do this. So we're going to use VPython to calculate this. So here we are at glowscript.org. And let's go to this public folder and create a new program here. And we got to give it a name. So we'll call it gravitational force. Okay, and let's make this font bigger here. And I want to show you how easy it is to do this in VPython instead of doing it with your calculator. So we don't need to be fancy and display any objects. All we need to do is just define some variables. So we can say, we can create a vector called r star, which is just the position of the star. So it's 0.5 times 10 to the 11, 1 times 10 to the 11, 0 meters. And the mass of the star is 1 times 10 to the 30th kilograms. And the position of the planet, it can be a little bigger, is equal to vector 2e11, 1.5 e11, 0 meters. And the mass of the planet is 5 times 10 to the 24 kilograms. And we need a value for the constant g, which is 6.7 times 10 to the minus 11 Newton meter squared per kilogram squared. And now notice that life gets simple fast, because we can actually we have a lot of vector calculations to do here. So we need the vector r, which is it? R planet minus R star, or R star minus R planet? Let's put a comment here. We'll start with force on planet by star. Okay, so the reason we're not using the POS attribute is because we don't have any objects. So if we made a sphere, then we could say star dot position, because position is an attribute of the sphere object. But in our case, we're not going to worry about a display with objects. We're just doing math, okay? So we just have naked vectors that aren't attached to any objects. Okay? So we're just using VPython as a calculator. If we want to display, we can get fancy and make a sphere and put it in the right place and all that stuff, and we may want to do that at some point. But for now, we're really just going to do a calculation with these objects. So again, do I want R planet minus R star for the vector R, or do I want R star minus R planet? Yep, R planet minus R star. Thank you, Mackenzie, because the planet is the system and the star is the surroundings. So final minus initial, you start at the surroundings, go to the system. And now we can ask VPython to do all that vector stuff for us. So we can go print R, we can just print the value R. We can print the magnitude. We'll just print magnitude of R. We can print the unit vector. Let's print hat of R. And we'll run this program And we see that I have to make the window, okay, I have to zoom out slightly. And we see that that VPython did all those vector calculations for us. We didn't have to square the components and take the square root, and we didn't have to then divide the vector by the unit vector. It did all the calculations for us. So this is by far the simplest way to do vector calculations in homework tests and quizzes. And so now we can actually calculate, put this all together, so we can say the force is minus g. So we've got minus g times what? The mass of the planet times the mass of the star divided by the distance squared. So the magnitude of r squared, it takes the magnitude of r before it squares it. And that whole thing we want to multiply by the unit vector r hat. Yeah, it eliminates calculator error if you type in a number wrong in your calculator and you don't realize it or whatever. So you have a complete record of every value you used, and you can look back and see if one was wrong, and if it was, you just correct it and rerun your calculation without having to go through all the calculator errors. And so now let's print the force. Anything in quotation marks, remember, is just printed as a word, a string. So anything in quotation marks, the computer just prints. So now we can run the program and we get here's the force we calculated. And if we happen to want the magnitude of the force, we can print that. So this is just an easy way to do calculations accurately and quickly. And okay, so Morgan, I understand your anxiety about this, but in fact, what you're doing here is exactly the same thing you'd have to do on paper. So you can't forget it. If you don't forget a step on paper, you're not going to forget a step here. So what we need is the vector that's the magnitude of the vector that's the position. So we need all this stuff before we can do the calculation here. And now, so we'd have to input those one way or the other into the calculator or whatever. Now I'm just typing this, but what I suggest that you do is you write down on paper exactly the calculations you want to do and then type them into VPython. If you don't practice, you won't get better at it, and then it won't be useful. So you have to take the leap and actually practice. So one way to do it until you're sure is to do it in VPython, but check on your calculator. The only thing you have to remember is how to create a vector. Okay, so, and you can type vec or you can type vector, it doesn't matter. I type vec because I get tired of typing, but you can type vec or vector, they're synonymous. And how to square something. So you have to remember that there's that. And I would be happy putting those things on the equation sheet if you like, just so you can get syntax right. You don't need, so why do you not need another set of parentheses here? It has to do with order of operations, really. So if I understand the question correctly, so it takes the magnitude of r first, and then it squares it. So do we need a set of parentheses around the numerator? As long as we're multiplying, we don't. If we were adding something, we would. Okay, so that's all there is to it. That's an extraordinarily short program, and you get a lot of bang for your buck here. Let's copy our result onto this. So I'm going to copy our results here. So we get that the force is equal to negative 1.27 times 10 to the 22, negative 4.24 times 10 to the 21, 0 newtons. And let's see if this actually makes sense. Is it in an appropriate direction? So in our coordinate system, whatever it is, we had the star at 0.5 in the x and 1 in the y, so that's the star. And the planet was 2 in the x direction, 1.5 in the y direction, so that's the planet. So the force ought to be pointing toward the star. So the x component ought to be negative. It's pointing in the negative x direction. That looks good. The y component ought to be negative. It's pointing in the negative y direction. That looks good. The force actually makes sense. So let's think about another aspect of this force. Yeah, I think that, yes, because gravity, so the question is the force of gravity always in the opposite direction to r hat? And the answer is yes, because of the way we've defined r hat and the fact that gravity is always attractive, but that's not going to be true for electric forces. So I wouldn't try to overgeneralize here. Just think about it being attractive. So actually, let's try a different. Let's change this question. We'll just make it up ourselves. Okay. So here's a poll question that we're just making up ourselves. So we calculated the force on the planet by the star. So which is true? So the magnitude of the force on the planet is by the star is less than the magnitude of the force on the star by the planet, because the planet's smaller. So that's 1. 2, the force on the planet is equal in magnitude to the force on the star by planet. Or 3, the force on the planet by the star is greater than the force on the star by the planet. So does the star pull, does the star pull on the planet harder than the planet pulls on the star? Is it the same in magnitude, or okay, so I have a question with 4 alternatives and we only have 3 here, so you shouldn't answer 4. So here's our poll. Which is true? The force on the planet by the star is smaller than the force on the star by the planet, it's equal to the force on the star by the planet, or it's greater. Now, in this question, I'm not asking you to guess. I'm asking you to use physics. And so what you need to do is look at the equation for the gravitational force and think about this. There's a slight majority for 2. Some people think that the star is going to pull harder on the planet than the planet pulls on the star. And at least no one hit 4, that's right. Okay, so let's see. So no one can help guessing, but once you've guessed, you have to use physics to check your answer. So let's look at these equations here. So here's our, that was the star, right? And this is the planet. And we have force on planet is equal to minus g mass of the star, mass of the planet, over the magnitude of r squared times r, we'll call this rps, planet minus star hat. Yep, Julian, you nailed it. So the force, so, and in this case, we have, if the planet's the system, we have our planet minus star. If we have the star and the planet, but now the star is the system, the only difference here is that this vector r star minus planet goes the other direction. So we're going to have r hat this way in this case, and we're going to have r hat that way in that case. But when we're talking about magnitudes of forces, we're talking about magnitudes. This is 1, and that's 1. And now we're taking a magnitude of exactly the same thing. The distance hasn't changed. The masses haven't changed. So it looks like the magnitude of the force on the planet is exactly the same as the magnitude of the force on the star by the planet. Again, Alexander, we're taking it at 1 instant. Okay, so how does that work? So this is called, this means that this is a reciprocal force. We call this reciprocity. The magnitude of his forces is the same. And how does that work? Well, one way to think about it is to actually think about the atoms these things are made up of. So let's take a planet that has only 1 atom and a star that's made up of 3 atoms. Now these atoms are neutral, but they do attract each other. So let's see. We'll call these atoms 1, 2, and 3. So this is the star, and that's the planet. So the planet feels a force from atom 1, and it feels a force from atom 2, and it feels a force from atom 3, and these are really enough in the same place that they're actually going to be equal forces. So the net force is just F1 plus F2 plus F3. What about the star? Well, atom 1 feels a force from the planet, and atom 2 feels a force from the planet, and atom 3 feels a force from the planet. So in the end, and the force doesn't change. The planet exerts the same force on each of these atoms. It doesn't get weakened because it has to interact with all of them. It exerts the exact same force on these atoms no matter how many there are. So if we think about it on the atomic level, this reciprocity makes sense. So the the magnitude of the force on the planet by the star is actually equal and opposite to the magnitude of the force on the star by the planet. Now, are they going to have the same effect? Well, we can think about the momentum principle. So momentum of an object in the future is equal to the momentum now plus F net delta t. So delta P is F net delta t. So if the star and planet exert forces on each other for the same amount of time, that means that delta P would be the same. But what about the change in velocity? Well, delta P of the star equals mass of the star, delta V of the star. Delta P of the planet is mass of the planet, delta V of the planet. So these things are equal, but the mass of the star is very big, and the mass of the planet is small. So for these things to be equal, we get a small change in the velocity of the star and a big change in the velocity of the planet. So I see Peyton's question from before about the difference that r being a different direction. So yes, that's exactly right, that the magnitude of these two forces is the same, but the directions of all the components change direction. No, the forces, their motion has nothing at all to, so motion doesn't affect a force. Here's our equation for a gravitational force. Okay, do you see anything in there that has to do with momentum or with velocity? So that force doesn't depend on momentum or velocity, it just depends on position. So the force is going to be, if they're in the same relative position, the force is going to be exactly the same whether they're moving or they're stationary. The effect of the force will be different whether they're moving or stationary, because if they're moving, then we have to account for the momentum that they've got right now contributes to the final momentum as well as much as the force does, where if that's zero, then it's only the force. So Marco, well, the net force, so the question is, if you have a spring that's on the earth or something, do you have to worry about the force of gravity? The answer is, when you're calculating the spring force, you're only worried about calculating the spring force. If you're worried about what's going to happen to the object that's experiencing that force, and there's a gravitational force acting on it, you've got to calculate that force too. Okay, so the net force is the sum of all the important forces.